In this lesson, we're going to talk about how to find the number factors of a general positive integer n. The starting point of such problem is the prime factorization, even though we don't exactly know how to use it yet. So for prime factorization, we know the form of n can be written as p1 to the power a1, p2 to the power a2, pk to the power ak, where p subindices I from I equals 1 to k are primes, and those ai's are bigger than or equal to 1 are the exponents or the powers of those powers. Okay, this is the prime factorization of n. And we have this form. But how from this form to derive the number factors? It's not very clear. So we're going to take some special cases and to see if we can derive some intuitions. So the first simplest case we're going to consider is n itself is just a power of a prime, p to the power a. In this special case, basically we are saying that for a general n, there's only one prime factor, and it has power a there. What are the factors for such a number? Okay, for this, it's actually pretty easy to list all the factors. The factors are going to be 1, p is a factor, p squared is a factor, p to the power a is a factor. So totally how many factors there are? It's a plus 1 factors. A different way of thinking about this is, what is the potential form for a factor of n? I claim that it only can be in the form of p to the power something. Okay? It cannot have another prime factor in this the form of the factors. And that's actually pretty clear. If you have a factor, let's say a factor k, has another factor more than the p, so p something to the q, let's say that has 1 there, okay? So if you can write a k is a factor of n, so that means n can be written as k times some other integer, let's say l, which equals p to the something and q to the 1 times l. Now, the right side is a factor of q, but n to the left side, n is to p to the power a, only has factor p there, right? So it's impossible. That means for n, all the factors are in the form of p to the power something. And now, for this p to the power something to be a factor of n, the something, let's say this is a b, b has to be less than equal to a and bigger than or equal to 0. So there are a plus 1 factors. The factors being p to the power 0 is 1, p to the power 1, p squared, all the way to pa, a plus 1 factors. So here we have for n is a prime to the power something, the factors are pretty easy to find. And the number of factors will be just the exponent plus 1. Let's think about a second special case. N is p to the power a times q to the power b. So we're generalizing the special case in example 1 slightly. Instead of just have one prime factor, we now have 2 prime factors, p and q. Each of them has powers a and b respectively. Let's see what are the factors for this n. So if you focus on just the factors in the form of p to the power, let's say k, we know that from example 1, the factors are 1, p1, p to the square, all the way to p to the a. That's a plus 1 factors. Similarly, for q to the b, there are 1, q to the 1, q to the b, b plus 1 factors. So these are the factors only involves one prime factor in the prime factorization. How about the cross terms? We know that p times q, for example, is also a factor of n, right? How many such forms there are? It turns out all those factors in this form are going to be in the product. p1 times q1 is, p1 times q squared is, p1 times the q to the b is a factor of n. Similarly, p squared times q1, p squared times q squared, p squared times qb, it's another factor. So what I'm saying here is all the factors I can write down as p to the something and q to the something. Let's using k and l. This can be written as, that's all the factors. And in here, k has to be less than equal to a, bigger than equal to 0. L is less than equal to b, and bigger than equal to 0. And this captures all factors of n, which is in the form p to the power a, q to the power b. So basically, we're asking how many such forms there are. But this is completely determined by the exponent k and l. For k, there are choices ranging from 0 all the way to a, inclusive. For l, it ranges from 0 all the way to b, inclusive. So total choice for the k, number of choices, number of possible k's, is from 0, 1, all the way to a. And for L, the k is in, let's say, this set. And L is all the way from 0, 1 to the b. So the number of k choices is going to be a plus 1. Number of L choices is going to be b plus 1. So total number of p to the power k, q to the power l possible things are, total number of factors is going to be the number of k times the number of l, which equals a plus 1 times b plus 1. Now it's pretty clear for a general case of n equals p1 to the power a1, p2 to the power a2, pk to the power ak, from what we learned from the case of n equals p to the power a and q to the power b. So we claim a factor k is going to have the following form if k is a factor of n. K is going to be in the form of p1 to the power b1, p2 to the power b2, pk to the power bk. There's some limitation of the bi's. b1 has to be less than or equal to a1, bigger than or equal to 0. b2 is going to less than or equal to a2, bigger than or equal to 0. bk is going to be less than or equal to ak, bigger than or equal to 0. Actually, this claim is really the general form of what makes a number a factor of another number. For the factor k, if you do the prime factorization, it's going to be written as p to the power something, p1 to the power something, p to the power something, all the way to pk to the power something. And those powers has to be less than or equal to the original powers of the number n. Now, of course, we're asking the question of how many such k's there are. But because given this constraints, each bi is going to be less than or equal to ai and bigger than or equal to 0, for b1, there are the number of choices going to be a1 plus 1, because the b1 can be 0, 1, all the way to a1. And for b2, there are number of choices a2 plus 1. And for bk, the choices only come from 0 to ak, and there are ak plus 1 choices. Now, each choice is going to be independent. So from the principle of product in terms of number of choices, for the number of k's, total number of k is going to be equal the number of choices for b1 times the number of choices for b2 times number of choices for b3 times number of choices for bk. And that equals a1 plus 1 times a2 plus 1 ak plus 1. So this is the form for number of factors for a general number n, when n can be factorized into p1 to the power a1, p2 to the power a2, all the way to pk to the power ak.